Hi students, seen till bit rate. So we had discussed data and signals. So today we'll continue with this transmission impairment. See, the idea of transmission impairment is whenever a signal is traveling through transmission medium, so everything doesn't go the perfect way like that we have thought. We think that sender is sending some signal to receiver, and the signals are received at the receiver's end in a similar way the sender has sent it. No, it's not exactly the same, because there are whenever the transmission is going on, so there is like a kind of impairment, probably because of three reasons. The main reasons is attenuation, distortion, and noise. So in a nutshell, if we talk about transmission impairment, what is transmission impairment? Transmission impairment says whatever the signals that are sent at the beginning, they are not actually received at the end of the medium. So mainly because of these three reasons. So if we talk about attenuation, what is attenuation? Attenuation is nothing but a loss of energy. See, otherwise also students, the data that we are sending is in the form of electromagnetic signals. So that waveform. So quite possible, some of the energy may get lost of from that signal only. So this is called as attenuation. So many a times that we see, like whenever data is transmitting, so the wire through which it is transmitting, it gets warm. So this is nothing but the electrical energy gets converted into heat. This is the only reason like attenuation is bound to happen. So in order to compensate for this loss, what we do is we use amplifiers to amplify the signal so that normalcy can be retained. So if we talk about the attenuation is measured in terms of dB, the decibel, and the formula is 10 log 10 P2 by P1. So this is what we were talking about when we are talking about attenuation. This is the original signal, and due to this attenuation, we get this signal. So as we can see, the original signal and the attenuated signal is not at all similar. So what we do is at point 2, we amplify it and we get the amplified signals, and we can see amplified signals are similar to the original one. So this is how what we do in order to nullify the effect of attenuation. Now this is a simple example, we calculate energy in terms of power. So this is what we are doing. This is what we generally do now at our residences, at our place, the electricity consumption, that's the power. So we calculate it by means of kWh, kilowatt per hour. So exactly the same way. So here is the example. Suppose the signal travels through transmission medium, okay, and its power is reduced to 1/2. So this means now the power is half of earlier one. So now we have to calculate the attenuation using the formula. The attenuation comes out to be minus 3 dB. So minus 3 means there is a loss. This is equivalent to losing 1/2 of power, 3 dB. Okay, now what happens is maybe now we have used the amplifier, and what amplifier is doing is amplifier is making an increase in the power by 10 times. So the gain of power amplification can be calculated in this way. So this comes out to be 10 dB. Now it is positive side. So we have gained. Earlier we were having a loss of minus 3. So this can be noted when we are making it half, like the power. So the attenuation, the loss is 3. And when we are making it 10 times, we can see even the amplification value is shown us as 10. So this is what we have done. We have done, say for example, it gets transmitted, and from point 1 to point 2, there is a loss of minus 3, and now at point 2 we are using an amplifier, so it is making an increase of 7 decibel of this attenuation thing, +1. So again at point 3 to point 4 there is -3. So -3 plus 7 plus -3. So in a nutshell, still it comes out to be the +1. So this is good thing. So this is what is explained here, whatever I have explained you in the last slide. So this is again like measuring signal power in milliwatts. Now here there is nothing but the simple value is it's a change in the metric gets changed. Now it is in milliwatts. So we can see this also, like the formula goes like this. dBm, the one calculated in milliwatt, is equal to 10 log 10, and the value of dBm is given as -30. So using this thing, because we were having 10 here, so it gets like divided here, so this comes out to be -3. So we can calculate this PM is equal to 10 to the power -3 milliwatts. Okay, now what is here? The loss in a cable is usually defined in decibel per kilometer. Okay, per kilometer decibel loss, dB per kilometer. If the signal at the beginning of a cable is -0.3 dB, has a power of 2 milliwatt. So like what is the power of signal at 5 kilometer? So this is again very simple, like the loss in the cable in decibel is -0.3 for 1 kilometer. So for 5 kilometer, this comes out to be -1.5 dB. All we have to do is we have to put these values in the formula. So the formula is goes like this: dB, the signal at the beginning. So this is like, you can very well judge, this is the attenuation that is like represented here. So for 5 kilometers, you are calculated the attenuation as -1.5. So 10 log 10 P2 by P1 is -1.5, and I believe one of the value is given to us, that is like P2 by P1 is 0.7. This comes out to 0.71, and yes, P1 is given to us. P1 is like 2 milliwatts, so we can calculate the P2 power at signal 5 millimeters. So this is about attenuation. Now what we can say about distortion? Distortion is basically the signal changes its form or maybe its shapes. So quite possible distortion can occur in a composite signal made of different frequencies. Each signal composite has its own propagation speed through a medium and therefore its own delay in arriving. So see, distortion, like when we are talking about the change in shape, so you can correlate like there is a change in phase also. Like in the next slide, we will be seeing by the help of diagram. We can see this. There is a composite signal that is sent. Of course, as you can see, the composite signal is made up of three sine waveforms: 1, 2, and 3. So these are the components. So if these get distorted, like my composite signal get distorted, so then further with the distorted composite signal, if I am like trying to extract the components like different single waveforms, so I'll see those single waveforms will be entirely different with these single waveforms, and there will be phase change that is quite possible. So we can see here, yeah, you can see this. This is the composite signal that we have received, and if I talk about the components in phase, first one is similar, but if you see the second and third, their phases are different. So this is the meaning of distortion. It like distorts the signal. So distorts means changing the phase in a composite signal. So when we talk about noise, see noise, if you talk about in literal term, so noise is something you are sending the data from A to B, and it's like apart from the data that you are sending, some other things are also added up with the actual data. So this is nothing but called the noise, because it is unwanted. That extra additional information, nobody wants that, and that has like that is there simply because of the disturbance, the noise. So this is the like formula for noise. Noise is basically measured in terms of average signal power upon average noise power. So as you can see, the signal noise ratio for like checking the noise, whether noise is there or not. So you can see the SNR ratio has to be higher. A higher SNR ratio means that the noise is very less, because you can see the average noise power is in denominator. So if the denominator has got a lower value, definitely you will get a higher SNR value. So higher SNR means lower noise value, and the vice versa. It means that with the higher noise power, obviously your SNR ratio will be, SNR value will be lesser, very lesser. So this is the concept point 1 to point 2. This is the transmitted medium. This is the noise. And after the noise is like added, so the received signal is altogether different. So this can be one of the cause for impairment. So this can be an example of high SNR and low SNR. As already told to you, high SNR says that the noise is less. The power for the noise is very less. And if you talk about the low SNR value, it means the power for noise is very much. And in both the cases, if we are talking about SNR and there is a presence of a noise, definitely there will be like certain element of noise, and we won't be getting the actual data at the receiver end. So this is the formula. The power of a signal is 10 milliwatt and the power of the noise is 1 microwatt. What are the values for SNR and SNR dB? So SNR has got a formula, the power of signal 10 milliwatts. So what you need to do is you need to like first convert into watts. So for calculating it into watt, what you can do is 10 into 10 to the power minus 3. 10 into 10 to the power minus 3 comes out to be 10 into 10 to the power minus 2 divided by micro watt. So this comes out to 10 to the power minus 6. And if you calculate that, this comes out to be, the value is SNR 10 to the power 4. It means 10,000 is the value for SNR. And if you talk about the SNR dB, so you can calculate in terms of dB by using this formula, because SNR is nothing but, again, it's a ratio of the power. As you can see here in the formula, it is nothing but the ratio of the power. So power again has a formula for dB values as like this one given here. So we can substitute the value here and we can calculate the value as 40. Generally in terms of generally the value is represented in terms of dB on. So you can convert it like this. So this is again one formula you can check. Now this is one very good observation uh, for a signal whose SNR value is infinity. What does that means? It means there is absolutely no noise in the channel. It's a noiseless channel. For this, like, see, even if like we are unaware of this thing, this is a simple mathematics. Any term when divided by zero gives you the answer as infinity. And here zero is the noise. So when noise is zero, we can say it's a noiseless channel. And we are bound to get the SNR value as infinite value. And however, this is again a very good observation. We can never achieve this ratio. This is a very idealistic scenario, not a realistic one. Again, there is a formula for noiseless channel if you want to calculate this. So this goes like this. For noiseless channel, the Nyquist bit rate formula defines the theoretical maximum bit rate, and this comes out to be 2 into bandwidth into log 2 L. So this is the formula we can use, and 2 into, like, we can see the bandwidth. Bandwidth we have earlier seen. What is bandwidth? Bandwidth is the highest frequency minus a lower frequency, and into it's given here into log 2 to the power L, base 2 and log L. So what is L? L we have discussed in the last lecture. L defines the levels, particularly when we talk about the digital signals. So we talk about like levels. So for one bit, like either 0 or 1. For two bits, like 0, 0, 0, 1, 1, 0, 1, 1, likewise. So we can calculate it using this formula. Again, this is something, it's a noiseless channel we are talking about. And for each level, we send 2 bit. There are 4 levels. So this L comes out to be 4 and the value is 12,000 bit per second. So what does this means? Like considering the bandwidth, if the bandwidth remains same, so the bit rate is like directly proportional to the number of levels we have. As you can see, earlier question we were having 2 levels, so we were getting 6,000, and now we are getting 12,000 for 4 levels. Now this is again one formula. Like what is the capacity? We always say like the highest data rate that we can send for a noisy channel. So Shannon gives a formula for this. It's like Shannon capacity. Capacity is equal to bandwidth into log to the power 2 base 1 plus SNR. So we can calculate this. Consider an extremely noisy ratio. See, now this is a very good observation for what can be the value of SNR for an extremely noisy ratio. Like you can very well check here, the SNR formula goes like this: average signal power divided by average noise power. So what it means is, for a noisy channel, so for a noisy channel, average noise power value will be huge. So like say for example, average signal power has some value, but the denominator is having a very huge value, very huge value. So you'll find that it is so huge that you can consider average signal power as 1. So 1 divided by a huge value, the answer will like almost equate to 0. That is the reason in the formula, we have that is the reason in this question, in the formula we have used the value as 0. Considering an extremely noisy channel in which the signal to noise ratio is almost 0. In other words, what we can say, the noise is so strong that the signal is almost like invisible. It gets fainted. So in that case, obviously, when noise is like anything and we are unable to send anything, so we can say even the capacity is 0. This means that the capacity of this channel is 0 regardless of when. This is again very critical observation. Now in this question, we were having bandwidth, we were having B bandwidth, but despite of the fact that we were having B bandwidth, our capacity is 0. So it is not like having a bandwidth is not everything that is required. I mean, the channel has to be there with a very minimum noise. Then only you'll be able to transmit. See, it's like very. I'll give you a small analogy. Say, for example, you are having a car and it can zoom past with the speed of 120. So ideally, like if you have to cover up a distance of 240 kilometers. So looking at the simple mathematics formula, it should take only 2 hours, but this is like next to impossible. It's like that road is not only available for me, it is like for the rest of the public of the society also. So like there can be noise, there can be traffic, there can be accident, there can be waiting time at the toll plazas. So considering all these things, bandwidth can never be equal to capacity can never be equal to bandwidth. Like in idealistic scenario, capacity is always less than bandwidth. So this is what is depicted here. In fact, in this particular example, it is depicted despite the fact we were having good bandwidth, our capacity is like not less, it is 0. So this is again one formula. Capacity we were supposed to calculate looking at the SNR formula, and I believe this we can do. So I am skipping it. Everything is given here. You can check that. Same goes here. Shannon formula needs to be used, and then you can calculate the value. So you can find it out. So the Shannon capacity gives us the upper limit, and the Nyquist formula tells us how many signal levels we need for transferring the data. Now, what can we say about the latency or delay? See, if we talk about the latency terms, what does it mean? It means that the entire message, whatever we have sent from the sender, how much time it actually takes to reach at the destination. So this is like latency, and latency includes everything like the propagation time, how much is the like the speed of the data by which it travels, plus the transmission, like again the channel on which it is transmitting, we have to take care of that also. Quite possible there has to be some waiting also, so we are categorizing it as queuing time, and then we can have processing delay also, quite possible. So latency is the sum up of everything. Now when we talk about the propagation speed, it is the speed at which a data travels through the medium from source to destination. And when we talk about the transmission speed, uh, it is like it takes care of the message size and bandwidth. So like formula wise it is given also, propagation delay is equal to distance divided by propagation speed, and transmission delay is equal to message size divided by bandwidth in bits per second. And this is the formula that we have earlier seen, the latency formula. So this is the formula. This is the example. A network with a bandwidth of 10 mega bits per second can pass only an average of 12,000 frame per minute. Now it's like the data is given in the form of 10 bits per second, and the framing is like per 60 minutes. So first we need to calculate it for second. So for 60 seconds it is 12,000 frames. So this comes out to be like for 1 second it comes out to be 200 frames. Okay, fair enough. So 200 frames in 1 second. Now we have to calculate the throughput. So throughput is basically the maximum data that we can transfer in 1 unit of time. So this we can see we have calculated is uh, 1 second on with an average of like 10,000 bits, we can send 2 MB per second of data, because like we were having 200 frames and one frame was equivalent to 10,000 bits. So 200 frames comes out to be 2 megabits per second. Now this is what you can see, despite of the fact that we were having a bandwidth of 10 megabits per second. This is what we are talking about in terms of transmission. We were having like now we are actually able to have a throughput of only 2 megabits per second. It is actually 1/5 of the maximum capacity, that was 10 megabits. So now I believe answer is clear to you. What are the reasons for this? The reason is probably the noise, the impairments, and other things. The throughput is almost 1/5 of the bandwidth in this case. Now this is again one thing, the formula wise it is given. The distance between the 2 points is 12,000 kilometer. The speed is this. What we are supposed to calculate is we have to calculate the time. So I believe for calculating the time, it should be distance upon speed. So tell 12,000, you have to convert it into meters and then divided by this. It is 2.4 into 10 to the power 8. Do not get confused. So you can calculate it. It's very easy. This comes out to be 50 milliseconds. So 50 milliseconds is the propagation time. Now same goes here. Like this is a small change, I believe. Otherwise, the rest of the information is same. And now what we have done is the bandwidth is available to us, and now we have to calculate one by one the propagation time and the transmission time. So I believe we have already calculated the propagation time. It comes out to 15 milliseconds, and now we have to calculate the transmission time. So transmission time is very simple. 2.5 kilobyte message is sent in 10 is sent on a network of 10 GB PS. So for 1 second, how much will be the time taken? So this comes out to be 2.5 into 10 to the power 3, because 1 kilobyte is like 10 to the power 3. And again, you need to calculate into bits, because GBps is given us in bits. So 2500 into 8 divided by 10 to the power 9. So this comes out to be 0.020 milliseconds. This is the answer. Note in this case the message is short and the bandwidth is high. The dominating factor is transmission. The dominant factor is the propagation time, not the transmission time. So we have to like very carefully look at both the aspects, that is propagation time and the transmission time. So this is one more example given for propagation time and the transmission time. If you compare it with the earlier example, the propagation time will remain same because everything is same. If you talk about the transmission time, the size is like increased like anything, and I believe yes, we can see the bandwidth is reduced. So we can calculate this using formula, and here like the transmission time is increased like anything. There are two reasons for this increase in transmission time. If you will compare with the earlier one, there are two reasons, and the reason is one, the size of the message gets increased, and two, the network bandwidth, like the available bandwidth, is reduced. So obviously this is very common to like judge that the transmission time will increase, and it has increased like anything. So we can calculate that. So there is one more characteristic, bandwidth, which we have seen, and here we are talking about bandwidths in two contexts. Like in the earlier classes, in the rather I should say the previous lecture, we have seen bandwidth in hertz because it was like FH, highest frequency minus the lowest frequency, and here we are seeing bits in bit per second, like the message which gets transferred in one particular unit of time with speed. So this is like explain here. Bandwidth in bits per second is often referred to as capacity, and here I have already explained FH minus FL is the concept. Now what is the throughput? Throughput is like how fast you can send the data, how much amount of data you can send. Here it is written like this. I have already explained you. Although at first glance bandwidth in bit per second and throughput seem the same, no, they aren't same because due to some noise and other impairment factors, throughput is always less than the bandwidth. A link may have a bandwidth of B bps, but we can only send T bps through this link. So which means like T is always less than B. I think this we have already covered. Now there is one more parameter, bandwidth delay product. Let us quickly jump to the example only, then we'll be able to understand this. See, this is the cross section bandwidth, and this is the delay. Like the product of all the both the things comes out to be volume. So this is the concept. Now this is very simple example. Say for example, sender has to send some data to receiver. Now what we are doing is we are saying we are having a bandwidth of 1 bit per second. Now what does this mean? Like in 1 second we can send maximum of 1 bit, and this we need to continue for 5 seconds. So that is the complete period. Like 5 delay is 5 seconds. So this first bit we have sent at 1 second. Then again we are like as the time is increasing, what we are doing is we are sending one more bits. So like after 5 seconds we'll see we have sent the 5 bits, and the bandwidth is 1 bit per second. So the formula is 1 into 5, and the answer is at the end of the day we have sent 5 bits. Now here what we are doing is we will be changing the data. Now instead of having 1 bit per second, we are using 5 bits per second. So the bandwidth is 5 times now, and the delay is same. So for every second we are able to send the 5 bits. So for delay of 5 seconds we will be sending total of 25 bits. So this comes out to be our throughput. So this is our throughput. So I believe we have discussed all these things: latency, bandwidth, transmission impairment, the capacity and the levels, simple composite signals, and analog and digital signals. So thank you guys. We'll see you in the next lecture. Thank you.